A very good afternoon to all. Welcome to today's session on information theory and coding. Am I audible to all? Anybody can type in the chat box. Is it audible? You are able to see my presentation. Kindly put in the chat box. Yeah, 2 members has replied. Yes, sir. Yes, sir. So okay. So we'll start this session for today. So in the last class, we had seen Unit 2's problem based on ternary channel, and we had seen an introduction to Unit number 3. So in today's class, I will be giving you a session on the Hamming distance. What is the purpose of Hamming distance? How do we go for this Hamming distance? What is the purpose of that? Its application, how to deal with Hamming distance. Okay, so let us go to the presentation. As we had seen in this Hamming distance, for that we have a specific terms to be determined, which includes your code words. So code words should be unique in nature, and this code words should be always more effective, and they should be unlike to each other. Okay, so the definition of this Hamming distance, I'll tell you within can be defined that these two, such that u and v, which we take the distance is being scripted as u of I not equal to v of I. Okay, so this is your description for that. I'll explain you. For example, I have an vector of having a m is equal to 3. If m is equal to 3, we'll be having a 2 power 3 possible combinations. So this 2 power 3 possible combinations are is equal to 8 if we consider m is equal to 3. So the ranges from 000, 001, sorry 000, 001, which is 1, then 012, which is 2, 011, which is 3, 101, which is 4, 100 is 4, sorry, 100 is 4, 101 is 5, 110 is 6, 111 is 7. So these are the maximum possible combinations for m is equal to 3. So 8 instances: 0, 1, 0, 1, 2, 3, 4, 5, 6, 7. So totally 7. So all these 8 form the vertices of a cube, as in this diagram, vertices of a cube, with Hamming distance to be varied from u to v. Okay, in graph theory. So we'll see that. So these are some of the properties of that. Always distance between u and v, Hamming distance should be greater than or equal to 0, with equality if and only if u is equal to v. equal to v, and d Hamming distance of u with respect to v will be always equal to Hamming distance of v with respect to u. Okay, and c is your triangular inequality. D with respect to W will be always less than or equal to D plus D of V, comma W, with a small problem, don't worry. So this is the proof of lemma. So, so the Hamming distance is being derived from Hamming distance is used for error detection and correction. So most probably most of you would be wondering what is this error detection and error correction is. So first we'll see this error detection and correction, then I'll tell you about Hamming distance. Okay. So what is an error? So error occurs when digital transmissions are being done. We'll be having an continuous signals. So those continuous signals will be converted into discrete signals. So and these discrete signals are being transmitted, manipulated, and being obtained. So in this, there may be an occurrence of error. So which we call it as digital system makes an error. Okay. So what type of errors that they do is that in a binary system, if I send 1, it will assume it has to be a 0. If I send 0, it will assume to be taking it as 1. So this is a type of error. And where do we all use these errors is that all the data applications require error-free transfer. Video, voice applications also require error-free, and this error-free region will give us better data rate. So eliminating the error is not at all possible, whereas we can reduce the error. Eliminating 100% of error is not at all possible, but we can reduce it by using some controlling mechanisms. So that we call it as error control. Error control. So error control is used when transmission system does not meet the required application. Whatever is our demand, that will not be met. So then error is being occurred. So in that case, we can use an error control. So the error control ensures a data stream that is being transmitted to a certain level of accuracy. We cannot, as said earlier, we cannot eliminate error, but we can have control over that. So there are two different approaches for this. One is error detection and retransmission that we use in ARQ protocol, automatic request protocol, ARQ, which uses error detection and retransmission of the whole set of data. Next is forward error correction, FEC. So all these two techniques you will be studying in detail in your data communication networks when you go for next year, or when you choose an error controlling subjects in your next elective, next semester elective. There you will be seeing in detail about these things. So first of all, the idea behind error control, what is that? We'll see that. All the data that are being transmitted will be in the form of data blocks which satisfies some pattern, which we call as code words. So if that pattern is not satisfied, then error is being introduced. If it doesn't satisfy the corresponding pattern, then error is introduced. So which results in redundancy and blind spot. So what is this redundancy is? A subset of all possible blocks could be converted into code words. A subset of all the possible blocks would be converted into code words. And blind spot is that when the channel transforms a code word into another code word. If I am assuming it is as, for example, as 011, it will change into 100. So invert of that, which we call it as blind spot. So this is your main thing to be determined. So this is your diagrammatic representation. User information is there, which is sends our data. We have an encoder. All the inputs to the channel satisfy certain condition or parameters on the channel, which is being given onto a channel. Then from the channel to the receiver will be doing. So again, the pattern checking will be done. Either CRC, PC, or Hamming, or any error detecting. If it is being satisfied, it will deliver it correctly, or else it will give an alarm. It will give us a notification that there is an error in the code words or in the block set of blocks of data. So this is a type of checking, single parity check, and most of you all are familiar with the parity check. Okay, we have two types of parity checking. One is odd parity, second one even parity. If the number of ones in the sequence of data for a particular time or for a particular symbol or for a particular range, if it is odd, we call it as odd parity. The number of ones present in the whole sequence of ranges, if it is 1, or if it is odd number, we call it as odd parity. If the number of ones present in the sequence, if it is gives you even number, we call it as even parity. So based on that, we can determine this check bits. Okay, we have information bits of b1, b2, b3 till bk. If the presence is odd, we take it as odd parity, and if it is even, we take it as even parity. Okay, we can do horizontal odd parity. This is what horizontal. This is horizontal. We can do even vertical, which will be in the form of row 1, row 2, row 3, row 4, row 5. In vertical, and even we can do horizontal and vertical together also. Some of the examples: information is 6 bits. For example, here we take, here information bits are, sorry, not 6 bits, 7 bits. 0 1 0 1 1 0 0 is the transmitted bit. This we want to transmit. So the parity bit will become in addition to that. So since there are 7, we need to add 1 bit to that. So which is 0 plus 1 plus 0 plus 1 plus 1 plus 1 plus 0. Okay, how do we determine this? Is that 1, 2, 3. So there are 3 ones. Okay, and this 3 ones corresponds. How do we add this? We need to use this addition. Don't go for direct binary addition. Use this addition. What is this addition is? Addition is called as modulo addition. And most of you all are familiar with modulo addition. Okay, modulo addition is what? Can anyone tell me what is modulo addition? Or let me put it in the chat box. Modulo addition is modulo addition. 0 plus 0 is what? 0 plus 1 is equal to what? 1 plus 0 is what? 1 plus 1 is what? Okay. If anybody is familiar with modulo 2 addition, can give me the answers for this. Either in chat box, or you can unmute and you can say 0 plus 0 in modulo addition. Modulo addition is nothing but usage of XOR gates in the addition. Okay, in XOR gate, what do you get for 0 plus 0? 0 modulo 2 or 0 XOR 0? No, 0 plus 0, I'll write it. 0 plus 0 is always 0. 0 plus 1 is always 1. 1 plus 0 is always 1. And 1 plus 1 is equal to 0. Yeah, you can check my answers. Anybody can check my answers. So model addition is using your XOR gate. Okay. Go back to this single parity. Do model addition. Do model addition. 0 plus 1, you get 1. 1 plus 0, you get 1. 1 plus 1, you get 0. 0 plus 1, you get 1. And 1 plus 0, you get 1. So the parity bit is 1 here. So this is to be added with your information. So this one in orange color, I think so. Yeah, in orange color is added to your information. So 0, 1, 0, 1, 1, 0, 0, as it is you write. And this parity bit you add it at the last. So this is your code word. This is your code word. 7 bits of information and 1 bit of parity checking. So this concludes your code word. Okay. Now, what do I do is that I introduce an error in the third bit of information. The third bit of information I have 0, 1, 0, 1, 1, 0, 0. Now I introduce an error. So error in the sense instead of 0 you will get 1. So I am writing it as 1. Okay. Now see the parity. See the parity. Parity is 1, 2, 3, 4. One more parity is there. One more 1. So totally 1. Number of ones is 1, 2, 3, 4, 5. So 5 we got. So there is an error being detected. There is a single error being detected. Okay. So when you count this code word, count the number of bits in this code word. 1, 2, 3, 4 bits. Only 4 ones are there. Only 4 ones are there. Okay. There are 4 ones. You will get an even parity. It is correct. But this gives you odd parity. It shows that it is an error. Understood? It shows an error. Now, in some examples, if rather than only one bit as error, if I introduce 2 bits as error, now I take third bit and fifth bit. I take this third bit and I take this fifth bit. 2 bits I am making it as error. Then this will eventually detect 1, 2, 3, 4 only. It will detect only 4 number of ones. It will be always an even, so error cannot be detected at all. Error cannot be detected at all. If there is a single error, we can easily detect. If there is only one bit of error in the message signal, it can be easily detected in the code word. It can be easily detected using your parity checker generator. If there are 2 bits of error, we cannot detect its error. So this is your conclusion for parity check or your parity codes. If only one bit is being errored, we can easily detect. If 2 bits, we cannot detect. So next comes a block diagram of check bits and error detection. So how to overcome all these things? All those things is that one bit error easily detect using single parity check, or using a parity checker generator you can easily detect. If there are 2 and more errors in the same information, how to check? So for that we need to have a systemic analysis. So the systemic analysis starts with check bits. Okay. So information Information is what? Our data that we are transmitting, which is k represented as k, and we are taking for the equivalent information will be checking the bits. Will you introduce some check bits? Okay, so check bits will be given to your channel. Will be given to your channel. So then after the channel, the information will be retrieved back to your user after comparing the check bits. So this comparison is a major task. So this check bits has to be compared. Okay, if any mismatch is there, it has to compare it again. It has to recalculate the check bits, recalculate until we get the desired information. So then, if information accepted, the information is accepted only if the check bits match. So whatever we are transmitted here, if this check bits matches, then information is sent, or else it will do checking, or it will say the transmitter to resend the bits again. So this is what check bits and error detection is. Next is redundancy. How far this single parity check works is out of our topic. So we will go for the next topic in this. Okay. Because evaluating, we will not be able to complete our unit 3 appropriately. So our main objective is to concentrate on Hamming codes. I'll share you all these materials. You can have it. So why we go for Hamming codes is in sequence. So kindly have it. Okay. So what is a good code? Good code is that code words, determination of a code words. So there are two scenarios. One is X represents your code words. Another one, circle represents your non-code words. So how far they should be present, in what distance or in what method if they are being present, such that we get good code combination. Okay, so the first thing is that good code is that having maximum efficiency is a characteristic, minimum redundancy is your characteristics of a good code. So how do we achieve this? Is that the many channels may have a preference for error patterns with fewer errors. So these error patterns may be mapped by using a code word to the nearby entity. And if these code words are close to each other, the code words are closer to each other, then detection failures will occur. The code words are closer to each other, they will obviously get failed. So each and every code should be separated by a distance. One code and another code should be separated by a small distance or some amount of distance. So these two diagrams represents how to separate them. You can see that these are non-code words, these are code words. All the code words together, no, it's poorer. All the code words afar will also be a poorer distance property. And if they are in intact with some space, you can see that this and this will have one, this and this will have one, this and this will have a one. This represents that from here to here we'll see this is present at the second, first and second distance. So the points between this x and this x is 1 2, this x and this x is 1 2 1 2 1 2 1 2 1 2. So the minimum distance between the one code and another code word should be separated by something. Okay. So this we call it as a good code. And I'll just skip the two-dimensional parity check, error detection. We'll go for the a type of codes that are used instead of code words. This is also another technique. Polynomial codes are used instead of vectors for code words. This polynomial arithmetic, instead of using checksums, and these are implemented using shift register circuits. Normal SISO, SIPO, PISO, PIPO shift register circuits can be implemented. This can be also called as CRCs, cyclic redundancy check. In introduction to unit 1, I had taught you about CRC. And this is where cyclic redundancy check or the polynomial codes are being used. These are powerful error correcting methods, mostly used based upon polynomial systems for data communication, which are used to detect the error as well as correct the error. So only we can correct the error once error is being detected. And in some cases, error detection only can be done by certain codes. Only certain codes will do error detection only. And only certain codes can do error detection as well as correction. Okay, keep in mind, detection is different, correction is different. Error detection, error correction. So let us have an example of this. I think you all are familiar with this concepts, mathematical tools. So I have a binary vectors mapping to polynomials. So consider addition of this. Consider addition. So I have x power 7, x power 6 plus 1. And I have x power 6, x power 5. I need to add this. So what is the procedure in adding is that we need to use this addition, modulo 2 addition. So write x power 7, x power 6, remaining plus 1 at last. Write it in descending order of its power. Degrees of power should be written in descending order. So this is the largest, so keep the largest first, then next. So these two are same, so keep it. And next x power 5, then x power 0, which is 1. Write it. So now, out of these two, x power 6, x power 6, what is common? X power 6 is common, so take it outside and I write it. So in between we have 1 plus 1. Okay, this 1 plus 1 is modulo addition. Keep in mind this 1 plus 1 modulo 1. So 1 modulo 1 is always 0. So we can write this polynomial arithmetic as x power 7 plus x power 5 plus 1 is the addition of these two polynomials. This is how we do polynomial addition in information theory. So next, multiplication. So multiplication is x plus 1 into x square plus x plus 1. So first, do our normal mathematical multiplication such that this x with all these coordinates, 1 with all the coordinates. So I separate it and write x into x square plus x plus 1, then 1 plus 1 into x square plus x plus 1. Now x into x square, you get x cube, then x into x square, and x into 1 x. Similarly here, x square x plus 1. So now do our modulo 2 addition for common terms. What do we get common? We get common as x square and x square, 2x square are there. So 1 plus 1 will be 1 modulo 1 will be 0, and x and x 1 modulo 1 will be 0. So remaining is x cube plus 1. So this is your polynomial multiplication. Let me see any doubts in this polynomial arithmetic or polynomial multiplication. Any doubts? I'll keep this polynomial multiplication for 2 or 3 minutes such that you can see. So after the polynomial arithmetic polynomials addition, I think the first one, first division, everyone are familiar, right? Everyone are familiar. Dividing 1,222 by 35. What do you get? Okay, one time you'll be dividing. Okay, three times if you divide. Sorry, 122. You can see it for three times. So you'll get 105, remaining 17. So two downside. So it becomes 172. So 4 times 140. So this is your divisor, this is your dividend, this is your quotient, and this is your remainder. So how do we write this? Using decimal numbers is that dividend, which is your result, dividend is equal to quotient into divisor plus remainder. So this is how do we write. Yes, obviously, I think everyone will agree. This is how we do division in normal decimal numbers. So now we take in terms of polynomials. we take in terms of polynomials. So polynomials, a sample I am giving you as divisor is x power 3 plus x plus 1 and dividend is x power 5 plus x power 5. So x power 6 plus x power 5. So how do I divide this? Is a question. I think this polynomial most probably you would have done in your mathematics also, and you would have asked your mathematical teacher, sir or madam, where do we use all these things? And you would have wondered for the answers. So this is where we use in coding. In coding, we will be using this polynomial system also as a method of coding. Okay.
Start box,
So
sir.
hello.
How,
Yes.
sir? How, sir?
For one,
How, sir?
start box,
How
sir.
we are using?
How?
How we are using that?
Just a minute. I am unable to get you. Yeah.
Okay.
Yeah. Chandra, your question is where we apply it in information coding, right?
Yes, sir.
Yeah. The answer, if you see in unit number 5, we'll be using cyclic codes. In cyclic codes, a method of solving the polynomials is being done, or we'll be doing it in a problem also. Don't worry.
Okay, okay, sir.
Okay. Still, this is the basic. Still, we haven't started how to solve it.
Okay, okay, sir.
In unit 5, we'll be solving cyclic codes
Thank you,
for
sir.
error detection and error correction also. Okay. So, shall we proceed? Polynomial
Yes, sir.
technique is a method for error detection as well as error correction. It is being best suited for that. We'll be seeing that in detail in unit number 5. Don't worry. Cyclic codes are a best example for polynomials, either in the form of addition, the form of multiplication, either in the form of division also. Okay, so now let's go to the dividend. Dividend is x power 6 plus x power 5. Our divisor is x power 3 plus x plus 1. Now, always whatever there is in the power should be added. Keep in remembrance. Whatever is there in the power should be added. So, what should I add in the quotient such that this x power 6 gets cancelled? Okay, here x power 3 is there. X power 3, x power 3. You will get x power 6. So, write x power 6. So, this gets cancelled. This gets cancelled. Now, then since we had wrote x power 3, combine that with x with the divisor. So, x power 4 you get. That with 1, x power 3. So, this is there as a reminder. This will remain. So, now bring this x power 5 down. Now you get x power 5, x power 4 plus x power 3 as the remaining terms from this x power 6 plus x power 5. Now, in order to cancel this x power 5, what we want to do? With this divisor, we need to divide. So, introduce x power 2. So, x power 2 into x power 3, we get x power 5. Then next with x power 2 into x power x is, okay, we need not do. Okay, we can write it as it is. Okay, we can write this, bring this down. X power 5 plus x power 4 plus x power 3, bring it as it is. So here it is x power 5. So x power 2, x power 3, x power 5. So x power 2 x is x power 3. So write in the state of x power 3. Then x power 2 into 1. So x power 2. So here it is. So cancel this x power 5. Next is x power 4. Bring it as it is. Everything should be in decremental order of degrees. X power 4, x power 3 also gets cancelled. X power 3 gets cancelled. So remaining is x power 2. So what can we add such that we get x power 4 to be cancelled is x. So x into x power 3, we get x power 4. So x power 3 is not there. Then x into x square gets cancelled. So x into 1 x. So for this dividend and divisor, we get remainder as x. This we get it as x. So x is your remainder. And q of x is your quotient. Quotient is your q of x. Remainder is your r of x. So always keep in mind that the degree of this r of x is always less than the degree of divisor. It should be always like this only. Degree of r of x should be always less than the degree of divisor. Okay, see that x power 3 is the divisors. Here it is x. So degree is smaller. So this is a condition in that. That was about polynomial arithmetic. Now, what is in polynomial coding? Okay, a code. This is where we correlate polynomial arithmetic with polynomial coding. So, polynomial coding, a code having binary generating polynomial, having a binary generating polynomial with degree n minus k. Hello. Okay, sir. Okay, sir. Okay, sir. சரி சார். இல்லை இருக்குன்னு நினைக்கிறேன் சார். நான் ஒன்றும் செக் பண்ணிடுறேன். ஓகே 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 சார். அது அது எப்படி சார் ஃபில் பண்ணி சப்மிட் பண்ணுறது தான் சார் தெரியல எப்படின்ட்டு சார். ஆமாம் சார். அதை ஆமாம் சார், தான் சார் கேட்கணும். ஏன்னா சப்மிஷன் நம்ம யூஸ்வலாக அவர்கிட்ட தான் சப்மிட் பண்ணோம் டாக்குமெண்ட்ஸோட. அது வேற இருக்கு. ஆமாம் சார். ஆமாம் சார். இருந்தாலும் சார். ஓகே சார். ஓகே. தேங்க்யூ சார். Sorry for the disturbance. Let me check whether. Okay. Yeah. The polynomial coding is that code will be having a binary generating polynomial with a degree of n minus k. Okay. So now you'll be wondering where this n minus k came from. N minus k comes from the block diagram that I had shown you. See here. N minus of the degree n minus k. Okay. The g of x will be written as x of n power x power n minus k plus g of n minus k minus 1 x power n minus k minus 1. So which is this degrees minus 1. Okay, then it goes on till the polynomial gets g of x to the square plus g1 of x plus 1. So this is how we write generating. This is how do we generate a polynomial. We'll see this with an example, don't worry. So if k information bits are being defined with a degree of with the polynomial of degree k minus 1, so then I can write I of x is I0 plus I1x plus I2x square plus I3x square till ik minus 2 x power k minus 2 plus ik minus 1 x power k minus 1. And the degree of the remainders polynomial will be always n minus k minus 1. The remainders polynomial degree will be at most n minus k minus 1 always with that degree. And g of x can be found out by this relation, which we get x of n minus k, I of x is equal to q of x into g of x plus r of x. R of x is your remainder, q of x is your quotient, and g of x is your generating polynomial. So here g of x is a generating polynomial. X of n minus k into I of x is your information. X of this is your information that we are transmitting. Okay, so I can write easily the code word. The code word as b of x is equal to x n power minus k into I of x plus r of x. So where this information is n, this is k, this is n minus k. So this you can see with a nice example. This is a good example of your polynomial coding, where the generator polynomial is given with k is equal to 4. If k is 4, n minus k is 3. So we need to generate n minus k. Now can you tell me what is n? I didn't mention it. Okay, so this is your 7 comma 4. 7 comma 4. So 7 is equal to n and 4 is equal to k. So I forgot to type it in this. 7 comma 4 encoder. 7 comma 4 encoder, where n comma n is equal to 7 comma 4, n is equal to 7, k is equal to 4. From that we can determine n minus k, which is equal to 3. Okay, this means that our information is 4 and our transmitted code will be 7. I'll show you. See here, the information which is given is in 4 bits, 1 2 3 4, and our transmitted code word will be 7. 1 2 3 4 5 6 7. See at the bottom, 7. Okay, so this is your 7. So this is an example for 7 comma 4. So we get 3 polynomial. We will be having n minus k is equal to 3. So how do we do this? Okay. So the generator polynomial for this is given as x3 plus x plus 1, and I of x is given as x3 plus x2. I of x is your information. So how do we write this? How do we write this? Is that, let us assume there are there are 4 informations. The given information is 1 1 0 0. So substitute that 1 1 0 0 in this I of x information. I of x is I of 0 plus I1 of x power 1, this I2 x power 2 plus I3 x power 3 till ik minus 2 x power k minus 2 plus ik x power k minus 1. In that, if you substitute, this is for your it starts from, this is for your 0th sequence, this is for your first sequence, this is for your next sequence, this is for your next sequence. Always you should see from right hand side or from the least bit. So this is your least. So this is why this is written in this order. This is written in this order. So in the place of I of 0, we have 0, so it is 0. In the place of next I of 1 into x, we have 0, so it will become 0. Next we have 1, so here it is I2 x power 2, so 1 into x power 2, so we have x power 2 here. Then 1 into x power 3 we have here I3 x power 3, so I3 is 1, so we get x3 plus, sorry, x power 3 plus x power 2. This is your equation of I of x, information equation. Now, in the given problem, they are taking the encoding pattern. The encoding pattern is taken as x power 6 plus x power 5. Generator polynomial is given as x power 3 plus x plus 1, and the encoding pattern is given as x power 6 plus x power 5. Okay. So divide using your polynomial series, we get remainder, and we get a quotient. As we have done, I think this is the same problem that we have done in this. Recall that x power 6, x power 5 is your encoding pattern, and x power 3, x plus 1 is your generator polynomial. X power 3 plus x plus 1 is your generator polynomial. So find the remainder, and we can easily find the transmitted code word. You can easily calculate the transmitted code word. You can verify with your binary also. Equivalent binary software. It is parallelly given. You can verify by doing binary division. Then in the next we'll be seeing about the pattern in polynomial coding. How do we do polynomial coding? That we'll see. So if the remainder is 0, for example, we had seen here for this generator polynomial and for this encoding pattern, we had got a remainder. In some cases, we may not get a remainder also. Remainder will be 0. So what do we do? If remainder is there, if remainder is not there. Okay. So the transmitted code for this can be written as from this. Our x n power minus k of information I of x is equal to q of x, g of x plus r of x. We had wrote this, right? Okay, this is our generator polynomial. This is your quotient. This is your remainder. So that we are going to write now. So for this problem, our bit being transmitted is x power 6 plus x power 5. So what is this x power 6 plus x power 5 is your q of x. Q of x. Write it as it is, as given in the pattern, plus your remainder. So remainder is this x. So write it. Okay. So the equivalent of this x is 1 in coding. So this is equivalent to 1. So we can write 0, 1, 0. 0, 1, 0. So equivalently we can write the given information. The given information is 1, 1, 0, 0. So write it as it is 1, 1, 0, 0. So we got 4 bits of information. So the check bits is the remainder x. So x is what? Value is 1 in decimal. So equivalent in binary 0, 1, 0. Okay, 0, 1, 0. So now you can see that if you count this transmitted code word, this code word consists of n and n minus k. Okay, it consists of 4, as you can see here. Consists of n, it consists of k, which is 4 bits of information. This 1, 1, 0, 0 is k bits of information, and n minus k is 3. So 0, 1, 0. This is your transmitted code word. This is how to determine code word using your polynomials. We had seen different concepts in Shannon-Fanon coding, how to determine code word. We had seen how to determine code words in Huffman coding, and this is another method of determining code words, which includes your check bits. Why we include check bits is to detect the error and to correct the errors. So this method is applicable. Equally in cyclic codes, we use this as a best method in cyclic code. So the polynomial pattern should satisfy this equation. All the code words which are being generated by polynomial coding should satisfy this code words. The thing is that all the code words should be a multiple of g of x. And I had already said about reminder. If there is no reminder at all, if the reminder is 0, then what do we state? And if the reminder is non-zero, what to do? Okay, if the remainder is 0, the receiver, we call it as an entl. It does entl function by g of x. Okay. And if it is non-zero, then the entl is not a code word. So this is what the conclusion, or this is the pattern to be followed. Okay, in the decoding segment. So next, moving on to the shifty distance. Okay. So this is an example of your cyclic redundancy check. And somebody asked where we use it, sir. So it is used in this type of modems. Cyclic redundancy check with 8 bits of information is used in AT and Bell Robotics modems. CRC with the 16-bit information are used in bisynchronous systems. And CCITT, circuit for Cyclic Institute of Telecommunication Department. With the 16 bits CCITT 16, which is used in version 41 of High Data Link Layer Control System HDLC. X modem, we use it in modem systems, CCITT 16-bit and CCITT 32-bit is used in IEEE 802 point all the standards, which will vary like this. It's an example. So we'll start from the higher. X power 32, X power 26, X power 23, like this. The pattern will be IEEE 802 point any versions use this 32-bit. And DoD, Department of Defense, in US they are using and version 42s. Wherever you use version 42 systems, we use this CRCs, and especially this CCITT 32-bit information. Okay. Now, actually coming to our topic, what is an Hamming codes. Okay. Why? Because we are dealing about Hamming distances. Hamming distances, so which leads to Hamming codes. So Hamming codes are a class of error correcting codes. Hamming codes are a type or a subdivision of error correcting codes. So this error correcting can be done only when error detection is being done. Okay. If error detection is done, error correcting can be done easily. So for detecting the errors, we require Hamming distance, and this Hamming codes are being generated or being done with this condition. So this is your Hamming distance, m greater than or equal to 2. This is your Hamming distance. M should be always greater than or equal to 2. This is your Hamming distance. So this Hamming code word of length will be always n is equal to 2 power m minus 1. 2 power m minus 1 with n minus k as your parity check bits. So we had done n minus k. So that is your parity check bits. For example, if I have m is equal to 3. So where do you get this m is equal to 3 is that in this example we have done this is that example. We have done our parity check bits as 3. N minus k is equal to 3. So that is your parity bits. Okay, m. So if m is equal to 3, the condition for Hamming distance is m should be always greater than or equal to 2. So I take for example m is 3. Okay. So then what will be my n? Simply substitute 2 power m. So m is 3. So 2 power 3, 8. 8 minus 1, 7. You get this. And how to find k? So k can be found out from this. K, the formula n minus k is equal to m. You can easily find k. Rearrange mathematical. So you'll get k is equal to n minus m. So n is known 7, m is known 3. So you get 4. So then we can find the code rate. Code rate is your redundancy. It can be found out by m bar n. M is 3, n is 7. So 3 by 7. So similarly do it for m is equal to 4, m is equal to 5, and m is equal to 6. And see what do you get. I'll give you 2 or 3 minutes for viewing this. You can have a check over this and try to find whether these are correct. Okay. Let me check any questions in the chat box meanwhile. Yeah, somebody said it 7. Yes, it's correct. 7.
Dinesh, 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 good afternoon. Sorry for trouble. Dinesh. Hello. Hello, Mr. Dinesh. Dinesh.
Have you checked it?
Dinesh,
Sir?
Dinesh,
Yes,
good
sir.
afternoon.
Good afternoon,
Sorry
sir.
for trouble. Sorry
Yes,
for
sir.
trouble.
Yes, sir.
How things are going?
Nice, sir. No issues, sir.
No issues.
Yes, sir.
Only for this now the students will be around 13, 18 only, is it?
Yes, sir. Total strength is 19, sir.
19. Only 13 students are there. 13
Yes, sir.
students.
Yes, sir.
So 13 for you now 2 means only 12. You are having
Yes,
two
sir.
systems. You are having two system with you. Mine one. So around 12 students only now. Is it? Around
Yes.
7 are absent.
Yes, sir. 7 are absent, sir.
Any difficulties? Things are going all right?
Right, sir. No issues, sir.
Okay. So the students are aware of the internal test.
Yes, sir. It has been given, sir.
Internal test is being
Yes,
informed.
sir. Information
From
is being
21st,
passed, sir.
from 21st onwards, the internal test.
Yes, sir.
Okay. Students, how you are feeling? Students, Pavan Chandra, how are you? Pavan,
Uh,
okay, Dinesh. Okay, carry on.
Okay, sir. Okay. Thank you, sir. So, are you getting these answers? Check it out. If you substitute m is equal to 4, you will be getting n as 2 power m minus 1. Substitute 4. So, 2 power 16. Sorry, 2 power m. So, it is 2 power 4. So, you get 16 minus 1, 15. And similarly, you can find n minus k. N is 15. M is 4. You will get 15 minus 4. 15 minus 11 as 15 minus 4 as 11. Then redundancy as 4 bar 15. And m is 5. N will be 2 power 5, which is 32. 32 minus 1, 31. And the k will be equal to n minus m. 31 minus 5, which is 26. M bar n, 5 bar 31. M is equal to 6. 2 power 6, we get it as 64. 64 minus 1, 63. K is 63 minus 6, we get 57. Then m bar n will be 6 bar 63. So this determining the distance, you can see that as the distance increases, you can see, find the values for this. 3 bar 7, what do you get? 3 bar 7 value we will be getting. Anybody, any idea? 3 bar 7? We'll be getting 0.43 redundancy. If it is 4 bar 15, we get 0.266 redundancy. If you do for 5 bar 31, we get 0.16 something, 16 redundancy. And if you do for 6 bar 63, we get 0.10, or I think so 0.09, approximately 0.1 redundancy. Okay. So from this, what I would like to illustrate is that as the Hamming distance increases, the redundancy tends to decrease. If redundancy decreases, what will happen? Efficiency will increase. Code efficiency will increase. So this is what I would like to illustrate. Okay. So now to understand this in a better way, we'll take an example. M is equal to 3. So which is obviously, we'll get information bits, 4 information bits. We take B1, B2, B3, B4. We take parity bits. Parity bits will be 3. So I am writing, so this is for an example, I am writing B5. We take B5 as B1, B3, B4, B6 as B1, B2, B4, B7 as B2, B3, B4. So we are taking for example. Okay. So there will be, since there are 4, 1, 2, 3, 4. 4 information bits. There could be a combination of 16 code words. Combination of 16 code words. 2 power 4, which is 16 code words. Okay. So these are the list of code words you'll get. This is simple. Use this format. Modulo addition of B1, B3, B4 for determining B5. I think everyone are familiar with modulo 2 addition. So here if I wrote it as plus, it indicates modulo 2 addition. Always in this also it is modulo 2 addition. So modulo 2 addition of B1, B3, B4 or B5. I want to determine this. So this is your tabulation. Kindly go through this tabulation and check. You will be getting this. Everything is modulo 2 addition. Nothing is binary addition. Modulo 2 addition, XOR gate operation. We'll be using modulo 2 addition. Then if you go for B6, B6 is B1, B2, B4. You can see that, for example, B6 is this. This is derived from B1, B2, B4. B1, B2, B4 you take. You'll get B6 bit. Okay. And B7 bit is obtained from B2 XOR B3 XOR B4. B2, B3, B4. So for this B2, B3, B4. Do XOR, you'll get B7. Appropriately, you can tabulate the information as this. Since we are having 2 power 4, 16 bits of information. 16 bits you tabulate one by one, one by one. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 in 8421 coding. So that information again should be repeated here, since code word is combination of 4 information bits plus your parity. Okay, B5, B6, B7 is your parity. B5, B6, B7 is your parity. So write it. So determine B5 using this, determine B6 using this, determine B7 using this. So we'll get this. And now correspondingly, how do I find weight of this code? So weight of this code, it depends upon the number of ones being present. Number of ones. So number of ones is no ones. 1, 2, 3, 4, 5, 6, 7. No ones. So 0. So here 4 ones. 1, 2, 3, 4. So 4. Here 3 ones. So 3 weight. 3 number of ones in the parity. So 3. Here 3. Here 3. 3. Here 4. 4. Here 3. You can see 3. Here 4. Here 4. Here 4. And at last you can see that it goes on till all the 16. So here last is 7 number of ones. So I write it as 7. So this is your weight, Hamming code. So I'll give you 2 or 3 minutes for reviewing this. I'll give you 2 or 3 minutes. For viewing this table such that you can appropriately decode the code words. Let me check for the chat box information. Yeah, how we wrote code word? Yeah, code word is what this one. Okay. So B1, B2, B3, B4 is as it is. So see here for the first one I'll explain. Okay, for the first B1, B2, B3, B4 is as it is. You should write as it is same. B1, B2, B3, B4. 0, 0, 0, 0. So 0, 0, 0, 0. B5, how do we get this B5 is that based on this modulo addition of B1, B3, B4. What is modulo addition of B1? B1 is 0, B3 is 0, B4 is 0. So you will get. So next, how do we get B6? B6 is obtained, this value is obtained by doing B1 modulo 2 addition B2 modulo 2 addition B4. So B1 is what? B1, B2, B4 again 0. So if you do, you will get 0 in the place of B6. தூர போயிடாத இங்கே then for B7 B2 modulo addition B3 modulo addition B4. So B2 is 0, B3 is 0, B4 is 0. So you get 0. B2, B3, B4. Okay, 0. So for each and everything you should do. This I had done it for 4 zeros. Similarly, you take for I'll take for this one 0 1 0 1 I'll take. So 0 1 0 1. If that is the B1 B2 B3 B4 information, I'll write it as it is. We should write as it is. B1 as it is, B2 as it is, B3 as it is, B4 as it is. Now B5 is B1 B3 B4. B1 B1 B3 B1 B3 B4. You'll be getting B5 as 1. B1 B2 B4 you'll get 0 modulo 2 addition. Similarly for B7 you'll get 0. So for each and everything you need to check. So that's what I am giving you 2 or 3 minutes for checking that. So check. Let me see. Okay, now understood, Shrikala? How do we write? It's easier. Only you need to know what are the check bits. What are the check bits for B5, check bits for B6, check bits for B7. If that is known, you can easily derive that. Derive the code word. So code word is a combination of information bit as well as the parity bit. Okay. For this problem, we have 4 information bits: B1, B2, B3, B4, 3 parity bits: B5, B6, B7. Okay. So next is to write it in terms of equations. So I think we'll see this error detection with the Hamming codes. I think time might not be sufficient for explaining this. Okay. So with this, I complete Hamming distance. You can see only 5 minutes. It will take some half an hour or so for doing this parity check equations. How do you write parity check equations? how to detect the errors. Error detection cannot be done very much easily, and especially I have taken 3 detections: single error detection, double error detection, and 3 error detection. How to do that and how to rectify that. That will take some time for explaining. Wait for a Hamming, which is our prior thing in unit number 3, Hamming distance. Okay, and the general Hamming codes, error correction using Hamming codes, and performance of the Hamming error, correcting or detecting ability. We'll see that in next class. So kindly be kindly be in line. I'll take attendance. So this is what all this proof. So whatever this proof of Hamming distance is, all this explanation that I had seen. Okay, so then we'll go for in the next class. After completing Hamming distance, we'll go for Shannon's theorem, then converse of Shannon's, theorems converse, then followed by some comments on Shannon's theorem, then the second half of the chapter, which we called as optimality. Okay, that we'll see. After completing Hamming distance, hmm? Rattan sir. Hmm. Kindly await, I'll take the attendance. Sai Srija,
Present, sir.
Sai Srija can leave. Srikala,
Present, sir.
model question paper for
Present,
what
sir.
you are asking? Srikala, something you are asking, model question paper, what it is?
Internal, sir.
First internals. That's what I said. No, next week I'll tell you
Okay, sir.
what mode of examination, how to write the first internal test. All those things I'll tell you next week. I said no in yesterday's class.
Okay, sir.
Next week I will let you know. Okay. Right. Reddy Kumar, K Vamsi, Kishore,
Yes, sir. Present, sir. Yeah, Kishore present, sir.
Vamsi, Kishore, Kishore. Okay. Kishore can leave. Manashwini, Surya Chandana,
Surya Chandana present, sir.
Manashwini, Surya Chandana.
Sir. Surya Chandana
Okay, you can
present.
leave, Ma, then. Harshita, Pranit,
Harshita present, sir.
Harshita, Harshita.
Present, sir.
Yeah, your name, please.
Harshita, sir.
Okay, you can leave. Praneeth.
సార్ వెళ్ళిపోయారా?
నువ్వు వేయదు అటెండెన్స్ చేసి సార్ లాస్ట్లో ఇచ్చి.
Praneeth Lakshman.
Present, sir.
Yeah, Lakshman can leave.
Okay, sir.
Okay. Kalyan Reddy, Praneeth. Okay. Tanuja. Tanuja, Naresh Reddy. Tanuja can leave. Tanuja can leave. Naresh Reddy can leave.
Present, sir. Present, sir.
Yeah, you can leave. Pavan Chandra Sashikar.
Present, sir.
Pavan Chandra or Srikar?
Pawan, sir. Pawan is present, sir.
Pavan Chandra can leave.
Okay.
పుట్టుపల్లి సార్
Purna Venkat Sai.
ప్రెసెంట్ సార్. పూర్ణ వెంకటేశ్వర.
Purna Venkat can leave. You can leave. Sai Srikar. Purna Venkat Sivasai can leave. Okay. Harshavardhan Vamsi.
Present, sir. Harsha present. Speaker already said, sir. You said him.
Okay, you can leave.
Okay, sir.
Okay, right. What about A Vamsi? Sai Vamsi? Who all are there?
Hello, sir.
Srikar, okay, you can leave. Yes.
C103 present, sir.
Manashwini.
Yes, sir.
Okay, you can leave, ma.
Okay, bye, sir.
Okay, Arsha, you can leave.
Okay, bye, sir.
Attendance is mad. Sai Srikar, you can leave.